Okay, I want to solicit a few ideas or examples. If anybody has something other than 90% 4 times that can get me to roughly 17.91, somebody want to share? Katie, you want to share? What did you say?
Take it by 67.5% once.
So you're saying if I start with 26.5 and I go to 67.5%, so I take it times 0.675 only one time? So go ahead on your calculator and try that out and see if Katie knows what she's talking about here. Times 0.675. What do you guys think? Pretty good, right? Pretty close. So, does anybody have another one?
I had one that got me just below 17.56.
Okay, what was it?
26.5 times 0.95 to the 8, or carried to the 8.
So 26.5 times 0.95?
Yep.
So we're doing 95% of it, and you're going to do it 8 times?
Yeah.
Go ahead and try that one on your calculator. 26.5 times 0.95 8 times. What do you guys think? 17.58? Pretty good? One more. Anybody got another one? Katie, you got another one?
Yeah. Take it times 82% twice.
Let's try 82% twice. Okay, 26.5. Move this up here. 26.5 times 0.82 caret 2. That also gets us pretty close, right? So, for those of you that are struggling here, we're basically picking up where we left off the other day when we said our standard form of our exponential is going to be y equals a times b to the x, where a is some original number, something we start with, the size of a dollar bill, the size of a coin, the amount of money you start with, the population you start with. It doesn't matter what it is. You start with some amount, and then you're going to take that starting amount times some number. This is our multiplier, or our rate, or our percentage, or whatever it is. If it's a copy machine, it's a percentage of something, right? So that would be our rate. And then this is the number of times we're going to do it, our exponent. Repeated multiplication. We're going to do it over and over and over and over again, whatever that number x might be. And when we do that, we will end up with some ending amount, some final measurement, or whatever we're measuring. So one way to think about this problem that you were just working on with the coin, if I show you the 26.5 times 90% 4 times, they said that was one way to do it, right? We'll just isolate the 90 and the 4. What do you get if you just take 0.90 times himself 4 times? Well, you get about 0.6561. So this part right here is giving me about 6561, roughly. Well, what other ways can I get 6561? Right? So if I call this my B value, this 90, if I call that my B value, and I call this my X value, what B to the X can give me the same thing? And there's there's an infinite number of possibilities that we could do here, right? So, for example, let's say I told you you had to use the copy machine exactly 7 times. Okay? If you're going to use the copy machine 7 times, what B value, if I use it 7 times, is going to give me that exact same decimal? And how would I go about solving for that? I'd take both sides of the equation to the 1/7 power, right? If I go like this and go to the 1/7, we did this earlier this year when we were solving equations. If I go to the 1/7 power and I take this guy to the 1/7 power, then I will have solved for b, because this is going to be b to the 1 if I multiply it out. So if I go 0.6561 and I go to the 1/7 power, I would enter 0.94157, about 94.16%, if I were to do it 7 times. If I were to do it 9 times or 12 times, it'd be something else, right? So before we can move on to the more complicated exponential growth and exponential function stuff, it is absolutely pertinent that you understand what the a and the b and the x do in the simple form. And then we'll get to a little bit more complicated forms with like money examples and stuff like that. Let me have you try, let me see, what am I going to do here? Let me have you try this. Let's do this on your computer. I'm going to have you graph a couple things. Let's graph these ones. You don't need to fill in this is directions to do it, paper and pencil. Let's jump straight to the computer. Notice I have y equals, I got rid of the a. There's no original, so a is just 1 in this scenario. Okay, so I just have y equals b to the x. On your computer, I'm going to write these down so I can... So we got 0 to the x. Try to graph these. 1 to the x power, 2 to the x, negative 2 to the x. Notice the negative is on the inside. And half to the x. I'm going to pull up my grapher, GeoGebra. If I try 0 to the x, what do you guys get? Can you see the graph? Is that an exponential equation or an exponential function? No, it's just a straight line across 0. Use a little bit of common sense. What happens if you take 0 times himself x times 0 times 0 times 0 times 0 times 0? You're just going to have 0, right? So is this guy really an exponential? I'd say no. It doesn't make any sense to use 0 to the x power. What about 1? Change the 0 to a 1. 1 to the x. What's it look like? So again, it's a straight line, and it goes across 1, because you know that if you take 1 times 1 times 1 times 1 times 1 times 1, doesn't matter how many times you do it, you're just going to get 1. So again, I ask myself, is that an exponential curve? Does it look like I can't remember if it was Avi or Benita. Does it look like the curve we saw the other day, where it starts slow and it goes up? Of course not. So is that exponential? No. Try 2 to the x. Does that one give us what looks like an exponential curve? Yes, it does. Notice that it starts out kind of slow, and then it just takes off and it goes. It's actually very similar to what we saw. Can't remember. Was it Avi or Benita that was doubling our pay?
I think it's Rita.
Was it? It was Avi? So that looks a lot like Avi's pay, right? 1 penny. She took it times 2 to get it to 2 pennies. Took it times 2 to get to 4 pennies. Times 2 to 8 cents. Times 2 to 16 to 32 to 64. And eventually, as you start to double things, it gets bigger and bigger and bigger. So, see if I have a green marker. Yes. I would say that is an exponential equation, right? How about negative 2? And again, I'm going to ask you to make sure that the negative 2 is inside the parentheses. If I put the negative out here, that's a different thing. What happens when you graph it? It doesn't graph anything. Does that make sense to you guys? Think about what's going to happen there. What happens if I go negative 2 to the 1 power? That gives me negative 2. Okay? So that would give me like this point right here. 1 power, negative 2. What happens if I go negative 2 to the 2 power? Positive 4, right? Because it's negative 2 times negative 2, which is positive 4. So that would give me this point. What happens if I went to the 3rd power? Nope. negative 2 times negative 2 times negative 2. Negative 8, which would be way down here. Somewhere down here, right? And then 4 would be positive 16, which would be up here. And then negative 32. My graph's going to go like this, right? It's going to be all over the place, and it's actually not even going to work on those numbers 1.5 and 1. So what I'm getting at is this guy is not going to give us an exponential graph. Not an exponential function, right? So what we're looking at is we're looking at these different values of b. 0, no good. 1, no good. 2, no problem. Negative 2, no good. Okay? What about 1/2? Does it work? I'm going to change my negative 2 to 1 divided by 2. Or I could use a decimal. I could use 0.5. Does it work? Yes, it does. Except this time, it's not growing. We're not getting larger as we multiply over and over again. We're actually getting smaller. And we talked about that the other day, like when I said I was going to walk towards the wall. This would be the equivalent of putting something in the copy machine and putting it at 50% and making it half of it, half of it, half of it, and so forth, right? So, why are we doing this exercise? If I look at all these different values, that I could have for B, what are my rules on B? It can't be negative, so negatives are no good, right? It's got to be a positive number. So B has to be positive. Can it be 0? Nope. So we know for sure my rules on B. Here's my rules. B must be greater than 0. Can't be equal to 0 and it can't be negative. We're cool there? So can it be every single number that is greater than 0? Everyone except who? 1. Because 1 makes no sense, right? 1 times 1 times 1 times 1 times 1 is just 1. That is not exponential. So it's got to be greater than 0, and it cannot equal 1. Every other number, we're good to go. If it's 1/2 or 1/3 or 1/7 or 1/9, no problem. If it's 2 or 3 or 7.6 or whatever, no problem. But it has to be any positive number that's not equal to 1 is what we're going to find out with our exponentials. So what I'd like you to try to do is use this idea of this a times b to the x format. See if you can write yourself an equation that goes with that information. Just write it on a piece of scratch paper. I'll give you a minute to do it. Think about what your A is going to be. Think about what your B is going to be. Think about what your X is going to be. Now the question is saying use N and T. So instead of X, you would use T for time. Instead of Y, you would use N of T. I don't care what letters you use. I'm more interested that you figure out the format. Remember, we're just looking for the equation here. We're not really solving for anything. So I might have confused you a little bit here. Out of the y, the a, the b, and the x. There's 4 guys here, right? There's an ending amount, a beginning amount, a multiplier, and the number of times we're going to multiply it. Out of those 4 things, which one is not given to us in the problem? The multiplier, the b. Do you guys agree? Do they give you the a? Yes. What is it? 80. Do they give you the y, the ending value? Yes. 180. Do they give you the x? How many times are we going to multiply this? It's going to be 6, because let's think of this as being annual. We're going to multiply it 1 time a year. Now, do deer mate and reproduce 1 time a year? No, not necessarily, but for the sake of this argument, we're going to pretend that they do, and it just happens on January 1st every year, whatever. Okay? So the only guy that isn't given to us is B, as in boy. See if you can figure out what the B is based on the information that's given to you. Probably going to want to use your calculator. When you think you have something, flag me down.
So I filled everything into the equation, solved for B.
Fantastic.
And then just filled that in.
Perfect. Anybody else got anything? What do you got, Emma? 2.15? Not. I think when you took the 6th root of. Oh, I know. Where'd you get that 100? Looks like you subtracted 80? But I don't think you want to subtract 80, because isn't it 80 times? It's 80 times b to the 6th. So you don't want to subtract 80 from both sides. What do you want to do? Divide both sides by 80. Otherwise, you're spot on.
That's the right divided.
2.25 equals b to the 6. Perfect.
Yep.
Very nice. So that's your multiplier,
Yep.
which you rounded, because I think it went on and on and on and on, right?
Yep.
Good. Okay. If I set this up in this format, I know that I'm going to end with 180. I know that I'm going to start with 80. I don't know what my multiplier is, so I'll just call him B. That's the one I don't know, right? And I know it's going to be to the 6th power. So now I just got to do a little algebra, and I got to solve for B. I got to get B by himself. So the first thing I need to do is get rid of that 80. Divide both sides by 80, right? So 180 divided by 80 in a decimal is 2.25. And that equals b to the 6th. And now you just got to know how to do exponents. How do I get a b to the 6th into a b to the 1? I'd have to take both sides raised to the 1/6 power, right? Because if I raise this guy to the 1/6 power, and I raise this guy to the 1/6 power, the 6 and the 1/6 just become a 1. So I'm just left with b on that side. So b is equal to whatever 2.25 to the 1/6 power is. And I have to do that on my calculator. And when you do that on your calculator, make sure When you do that on your calculator, $2.25, this is different. Some of you might already see what's going to happen to me when I do it this way. That is not going to give me the correct answer. Do you see why? Order of operations says I'm going to take the exponent first, 2.215 to the first power, and then I'm going to take 2.25 and then divide it by 6. No good, right? I've got to have it in my parentheses like so, otherwise it's not going to work. So what's my multiplier going to be? 1.14471423 blah blah blah. Okay? So now if I know that my multiplier is going to be that number, I just rounded it to 4 decimal places for the sake of saving room when I write it down, but we know we want to be careful when we round when we're doing exponential growth. I know that my multiplier is going to be that number, so now I could figure out the population of the deer at any time by taking my original amount, the multiplier that I just got, and now I can make t be whatever the heck I want it to be. 8 years, 12 years, 20 years, doesn't matter how many years I want to do, and I can produce that final amount, right? So that is, again, just your standard form of taking an original and multiplying it times some multiplier some number of times, x number of times. So if you wanted to graph this guy, 80 times 1.1447 to the t, we could visualize what it's going to look like. I will type it in here. So we've got 80 times 1.144714243. I'll put a bunch of decimals in there. Raised to the, got to use x instead of t, x when you're using your computer, the x power. Hit enter. There's my function. And I can't see it because I'm starting at 80, so I got to scrunch my graph down so I can see the number 80, because that's where it starts. Sure enough, there it starts at 80, and then now you can recognize the exponential growth curve, just like AV's pay scale, right? They're going to, this deer population is going to grow exponentially. Let me give you just a couple more like real examples before I have you work on something. Check this one out. I'm interested that you understand things such as compound interest. And this isn't a personal finance class, but if there's one of, I guess, a pet peeve that I have with what I'll call young people today, is that a lot of them are financially illiterate. There's plenty of old people that are financially illiterate too. Let me just give you a little idea of what I'm talking about. So personal story time here. Back when I was a high school teacher, I was offered health care as part of my benefits package, along with my salary and whatever benefits package comes with a job, right? And I could either take that health care, or I could choose not to take it and just pay for my own health care and or health insurance. And if I didn't take it, they would take the amount that they were going to give me to pay for my health insurance through the school's program, and they would just put it into like a retirement fund for me instead. Well, I did the math, and they were going to give me, I can't remember, $300-400 a month to pay for my health insurance. But since I was young and single and whatever, a single plan for a non-smoker who was only 20-some years old was only like $110 a month from Blue Cross Blue Shield. So, do I pay $110 a month out of my own pocket and then have my school take $300 or $400 a month, whatever it was, and put it into an account for me? Or do I just take the free health insurance? What do you think?
Retirement account.
You like the retirement account idea? The retirement account idea is going to cost me more upfront, right? I'm going to have to pay $110 every month to buy my own health insurance. But what's the benefit of that? I'm going to get $400 a month given to me for free, but I don't get to spend any of that money until I'm 59 and a half, which is when the IRS says you can take money out of an IRA without paying a tax penalty, right? So I'm not 59 and a half. I'm not even close to that, okay? But I took the IRA route, and I taught at that school for 4 years. So for 4 years, they were giving me money. So like for about 48 months or 45 months, they were putting money into this account for me. And when I left that school district and I came to teach for VCSU, I got to take all that money and I got to give it to Vanguard and put it in an IRA, and I haven't touched it since. Okay? And you can see what happened. I got to VCSU at about 11 years old. I can't remember the exact amount that was in there, somewhere around $20,000. And today I checked it just before I came to class. That account is now worth that today. So I went from 20,000, write it down here so we can pull it up. I'd like you to try to graph this. And 56,401. This was my beginning. This was my ending. Okay? So just go ahead and plot 2 points on your computer. I'm going to do a new file here. New. Go ahead and plot the point 0. So we'll call time 0 the time when I left, and we'll say $20,000. And then 11 years later, so I'll go 11, comma 56401. Go ahead and get your screen so that you can see those 2 points. So you got to scrunch way down because 20,000 is way down there. Okay. You got it so that you can see your 2 points? Should look something like mine. It starts at 20,000, and then this one's at 56, 11 years later. So the question is, if I were to connect those 2 dots, does it connect in a straight line? Does it connect in a curve? Is it quadratic? What kind of shape did I go from there to there? To exponential, right? Because we know that as money grows and through percentages, and so this IRA it's invested in stocks and bonds and a whole diverse fund, whatever, that grows exponentially, right? So how do you figure out what it looks like? You can use your fit feature. Remember that handy function that we have on our computer called fit, F-I-T? Fit, EXP, stands for exponential. Try your fit exponential. Okay. And then the points that I want are just A and B. So I'm going to go A, comma, B. And there you can see the exponential curve of what that account has done. This would have been back in like the year 2008, roughly. Was 11 years ago. Up to today, which would be point B. And there you can see what's going on. Now, your computer produces this little guy E, which we haven't even talked about yet. We'll talk about that in a second. But this is our B, or this would be like our B value or our rate, 0.09. Does that make sense, those of you that pay attention to finances? 0.09 is 9%, right? Anybody dabble in the stock market? Nobody? Historically, last 50 years, what's the stock market done? Good, bad? Anybody know what kind of rate of return you get in the stock market? See, this is what I'm talking about, people. You need to be thinking, I know right now you're paying tuition and working part-time jobs and probably don't. You need to understand how this works so that when you do get old like me, you've understood how to save some money, right? So you can retire someday. Stock market averaged roughly 10% over the last 50 years. What am I getting? About 9, right? Since then. It's more than just stocks in there and whatever, but to give you an idea. But the fun part, especially if you're into compound interest and mathematics and whatnot, is to look at where is that graph going to be 20 years from now. So if I go out to like 31 or something like that. So I'm going to sink it down, sink it down, sink it down. Now all of a sudden, that decision that I made back in 2004 through 2008 to pay for my own health insurance, it looks like it's going to start to pay off, right? Because when Jamie retires in 20 years, or when it, no, 20 years, well, we won't go there. But in 20 years, look at what the value of that's going to be. Now, I'm not a rich person by any means. I'm running on a teacher salary here. But if you understand the power, and I have many more retirement plans than just this one, but if you understand the power of exponential growth, now all of a sudden I changed $20,000 into $372,000 and I haven't done anything. I've just let it sit in an account and ignored it for 30 some years, right? So that's what I'm trying to express to you is this power of exponential growth. Whether it's population or money or bacteria or whatever it is, understanding how that curve goes, just like the Desmos that we did on Wednesday. So what we're going to do is I'm going to give you a little project that deals with these two formulas, and you might be familiar with these two formulas. Let's look at the top one. This is all in your textbook, by the way, if you want to look at some more of the labels and whatnot of what's going on here. Let's pick apart that top formula. Okay, let's start with P. What is it? The starting amount, exactly. This in our y equals ab to the x example, this would look like this. Y equals ab to the x, if I write it in over the top. So the P stands for principal when you're talking money. That's the amount of money you start with. Okay? What is R? Interest rate, the rate of increase. It's like our multiplier, right? So if you're getting 9% on your money, you don't take your money times 0.09. That would make it smaller. If I take it times 0.09, that just gives me the interest. But you also get the money that you started with. So you don't just take it times 0.09. You take it times 1 plus 0.09, right? Because you get 100% plus whatever the money is. Now, we all know that sometimes the stock market goes down too, right? So over a given year or span, that rate could actually be negative, not positive. But I'm not going to go into dollar cost averaging. You guys take a personal finance class if you want to understand that. What's the N? Number of times compounded per year. Now, we haven't talked about that yet. When we did the deer population, we just did it one time a year, one time a year, one time a year. But sometimes accounts compound every month. So maybe 12 times a year, it compounds means you get to take your interest, put it back on top of your principal, and now you have a larger number to gain interest with, right? That's what compounding means. So N could be, if N says monthly, N is 12. If N says quarterly, that's 4 times a year. Semi-annually, twice a year. Daily, N would be 365, right? So N can be any number. And then finally, we're going to take it, how many times are we going to multiply it? Well, T is always in years, but if we did have an N value, if it was, say, monthly, then it'd be 12 times the number of years. So if it was 10 years, it'd be 12 times 10. We'd do this multiplication 120 times. But you don't get the full rate. This is an annual rate. You get the rate divided by however many times you do it. So if you're getting 12% and you're doing it monthly, 12 divided by 12 would be 1%. You get 1% every month. Okay? So that's a compound interest formula. And then, of course, A is the final amount that you have when you're all said and done. Right? This is the exact same formula Except what? Anybody recognize it? What's the only difference? There's no n's, and there's an e. Somehow we changed a bunch of n's into an e. Anybody know that one? That's pretty high level stuff. Anybody know what e is? There's a button on your calculator.
Base power of 10 or something.
It's not base power of 10. You guys find the button on your calculator? It's just a number. Just like pi is just a number. You guys have all heard of pi. What's pi? It's a long decimal that goes on forever that's about equal to 3.14. It comes from the ratio of a circle's circumference to its diameter. It's how many diameters it takes to go around a circle, 3.14. E is similar in the fact that it is a decimal that goes on forever, but it's not 3.14. What is it? Did you guys find it on your calculator?
2.7.
It's about 2.718. And where does that come from? Well, the quick of it is, if you take 1 plus 1 over n to the n power, and you let n go to infinity like a massive number, so it'd be 1 plus 1 over a trillion to the trillion power, it converges to this number 2.718 blah blah blah, which we just call e. So the difference between the two formulas is this one is what we call compounding continuously. Like every split second it compounds over and over and over and over again. So a way to think of it is if n just goes off to infinity, like millions and billions, through some fancy math, it becomes this formula. So you have two formulas to use. If you're using one that says compounded monthly, daily, weekly, quarterly, something like that, you're going to want to use this guy with the n. If there is no n value, and it says it's just compounded constantly, like that's what bacteria does. When bacteria grows and grows and grows, they don't wait every month for the banker to compound their interest, right? Bacteria just naturally does it on its own, okay? That's what we call compounding continuously. And then you're going to be working off of this guy here. So what I'd like you to do, and this won't take you very long, and you can get started on it today, is on Blackboard, if you go underneath course docs and links, there is financial models on GeoGebra. See that document right there? What I'd like you to do is follow the directions on this. You're going to build a financial calculator that would be similar to like what I showed you with that IRA, where you can just input some starting amount, and then you can choose your interest rate. You can choose your whether I want you to make one that's both for the compounded with the n and the one that uses the e. And then when you're all said and done, you should have something on your GeoGebra that looks like this screenshot right here. Notice I have two graphs. This is just a snapshot from GeoGebra. Okay, let's review quick. P, what is it? Principal, starting amount. I made a slider where I could slide it to any starting amount. Okay? R, rate. When you do R, if I say 8%, you don't enter the number 8 for R. You enter the number 0.08. We have to do it as a decimal, not a rate, because percent is per 100, right? So when I have 0.0875, that's 8.75%. N, number of times compounded per year. So right now, this particular one was set to 4, so that would compound every 3 months, or 4 times a year, or quarterly, if you want to think of it that way. So notice my two equations. The black one goes with this one, and the red one goes with this one. Both of them started with $90,000. This one uses E with my rate. This one uses my rate, but then it also uses the N, which is the 4. So what I want you to do is not just use 90,000, 8.75, and 4. I want you to make sliders so that you can adjust those numbers to any numbers that you want. So follow the directions. And have that GeoGebra file ready to go by Wednesday. And we'll see you then.